So we're going to look at a couple examples here. In this one, we've got a balloon where air is leaking out of the balloon at a rate of 230 pi cubic centimeters per minute. I'm not going to read to you. You can pause it and read the question. So we're going to go through some steps here, but eventually these steps are going to go away. But we do have these to kind of walk you through how I think you should look at one of these problems. So first they say we should identify all variables involved in the problem. So we've got V represents the volume of the balloon. So we have V represents the volume of air in the balloon. R will represent the radius of the balloon. 2 L's. Identify which, if any, of the variables in the problem remain constant. So this is an important step here. We'll talk about why later, but you have to picture. Remember, calculus now we're talking about it as it's kind of the study of change, and again, you know derivatives as slopes of tangent lines. We've got that figured out. You guys are good at that. We now have to look at a different way we can think about a derivative. It is a rate of change. And so when things are changing, again, they're going to be changing at a rate with respect to time, just kind of reviewing some of the stuff we talked about in the last video. So when we go to find the derivative, we're going to want as few variables as possible to make our job a little easier. So we have to picture this balloon in motion. As I said, things are changing. So as the air is leaking out of the balloon, what is happening to the balloon? It's getting smaller. So if either one of these variables are not changing, we can just treat them as constants. So you have to imagine the balloon shrinking and losing air. The volume will be changing. The amount of air in the balloon is decreasing, right? So that's going to still be a variable. The radius of the balloon, if you imagine the length from the center of the balloon out to the edge of the latex on the balloon, that is also decreasing that length. So the radius is also still a variable. So in this case, neither volume nor radius remain constant. In the future, we're going to be able to pick out some things that remain constant, and that's going to be very helpful. Number 3, identify the rates that are given and the rates that you wish to find. So they mentioned 200, well, let's look at the question. They mentioned 230 pi cubic centimeters per minute, and they mentioned the radius is 4 centimeters. Which one of those would be a derivative or a rate of change? We're going to look at, if we're focusing on units, centimeters per minute is a rate of change. Per there is going to be the key. So they're telling us the rate of change of something. There's a couple ways to pick out what it is they're telling us. Are they telling us the rate of change of the radius or the rate of change of the volume? Again, I'm going to look at the units given to help me figure that out in this case. So that's kind of the first way you can look at this. It's cubic centimeters per minute. So it's a volume divided by a time. That's a dV over dt. Cubic centimeters is a volume changing with respect to time per minute. So dV dt is equal to 230 pi cubic centimeters per minute. And if you don't identify if you don't identify your cubic centimeters per minute correctly, or if you don't identify them at all, you're going to lose points. You need to give me the units, and they have to be the proper units. I guess that's the word I was looking for, units. dr dt, they don't mention it. They mention the radius is 4 centimeters. How do I know that's not a rate? It's not centimeters per something. It's not a rate. It's just a measurement of length, centimeters. So dr dt is what we're trying to find. This is why the equation we know for this is not good enough. So step 4 says write an equation, often a geometric formula or trigonometric equation that relates all the variables in the problem. So we're talking about a volume of a balloon here, volume of a sphere. So we're going to use that formula, volume of a sphere. Remember what our goal is here. We're trying to find the rate of change of the radius. this formula, this pre-calculus formula, is not good enough. It's a static formula. It doesn't have rates in it. So it's not going to help me. Well, it will help me, but I'm not going to be able to use this equation, this relationship between volume and radius, to find the rate of change of radius. I need a better equation, one that relates the rates of these units, of these quantities. So I want an equation that relates the rate of change of volume and the rate of change of radius. This way I can solve for what it is I'm looking for, the rate of change of the radius. So we're going to take the derivative of this, and that's how we come up with that equation. So the derivative of v is 1, and we're going to chain rule that with respect to time, so then it's times dv over dt. The next part of it on the right side, remember that 4/3 pi is just a constant, so we're doing power rule on r cubed here. The 3 comes down and multiplies by that constant, so we get 4 pi, and then we're going to recopy the r and reduce its power by 1, so we get 4 pi r squared, times, we're going to chain rule the r again, the dr over dt. And remember that those have meaning now, those dv dt's and dr dt's. Well, they've always had meaning, but now they have a different meaning in context of a word problem. So let's plug in what we know. You treat dv dt and dr dt now as quantities where you can plug stuff in for them. So do we know what dv dt is? Yes, it's negative 230 pi. That's the rate of change of the volume. That's the rate at which the air is coming out of the balloon. 4 pi r squared, so we have to talk about r. All right, so remember that we're talking about a rate of change at an instant. That's the magic of the calculus here. So we have to identify an instant. So as this balloon is changing, the rate of change of the volume is staying constant. They're saying it's always leaking out at the same rate. But the rate of change of the radius will be changing. At first, I imagine the length of the radius will be decreasing a little more slowly. But as the balloon gets smaller, I can kind of envision that radius is going to rapidly evaporate. So that rate of change of the radius is always changing. So we need to find it at a certain instant. So the problem has to sort of freeze in time for a second, and we're just talking about all the quantities at that moment in time. A key thing to note here is you can't really think of it like that until you have your related rates equation. So we're going to plug in an r. That's how they tell us a moment in time. They're going to say when the radius is 4 centimeters. But that can get confusing. Students want to plug that 4 in for r before we differentiate. So we have to wait till after we have our related rates equation, because remember, over time, that radius is changing. But now that we have our related rates equation, we can plug in any information we have. And we know that they're saying we're going to freeze it in time when the radius is 4 centimeters. So we're going to plug that in for r, and we're trying to solve for dr dt. So now this becomes, a basic algebra problem. We're going to solve for the unknown dr dt, and that will represent our rate of change of the radius at that time. We expect that you should kind of know going in, we expect that rate of change of radius to be negative because its quantity is decreasing, right? We can go back to our knowledge of derivatives there. When f prime of x is negative, that means f of x is decreasing. So it's the same idea here. Dr dt is the rate of change of the radius. We know when the rate of change of the radius is negative, r is decreasing. So when we picture the balloon deflating, it's really what we know is r is decreasing, so we expect the rate of change of the radius to be negative. So you should sort of think about that before you solve and make sure you've got stuff done correctly, like a little gut check when you're done. So I'm going to solve here for dr dt. You should pause the video and try to get ahead of me and see if you get it right. Okay, so welcome back. We're getting negative 115 over 32 centimeters per minute. Don't forget your units. Radius is a length. It's measured in centimeters. It's not measured in centimeters squared or centimeters cubed. It's centimeters per minute because it's a one-dimensional length.